Welcome to Brain Vision.
So firstly, if we have steam at 100 degrees Celsius and then cool it down to skin temperature of 34 degrees Celsius, the heat that is released into the skin, Q, is equal to M, the mass of water initially at 100 degrees Celsius, or the mass of steam initially at 100 degrees Celsius, times minus LV, where LV is the latent heat of vaporization, and this is negative for a vapor to liquid phase transition, plus C delta T, where C is the specific heat capacity of water and delta T is the change in temperature. So we have these values. So the mass of steam initially is 25 times 10 to the minus 3 kg. The latent heat of vaporization for water from our table is 2.256 times 10 to the 6, and that's joules per kg. And this is plus the specific heat capacity of water is 4.19 times 10 to the 3 joules per kg Kelvin. And this is multiplied by temperature change. Going from 100 degrees to 34 degrees is minus 66 degrees Celsius change in temperature, or minus 66 Celsius degrees. And so, since we have our values, once we do this calculation, we see that the heat released by the steam onto the skin is minus 6.33 times 10 to the power 4 joules. So the steam at 100 degrees Celsius, which is then cooled to body temperature, releases 6.33 times 10 to the 4 joules into the skin. How does this compare to water that is at 100 degrees Celsius? Well, the heat that is released into the skin for water that is still in its liquid phase is simply mc delta T. And so the same mass of water is 25 times 10 to the minus 3 kg into specific heat capacity of water, which is 4.19 times 10 to the 3 joules per kg Kelvin, multiplied by a temperature change again of minus 66 degrees Celsius. And doing this calculation, we get that the energy transferred from the water to the body when the water is cooled from 100 degrees to 34 degrees is 6.91 times 10 to the 3 joules. The minus sign just tells us that the energy is being absorbed from the water into the body. So looking at these two answers, we can see that the answer for A is much higher than the answer for B. So what does this tell us? It tells us that the total heat released by the water that starts as steam, so the total heat, we'll call this QS, the total heat released by the water that starts as steam is almost 10 times greater than the total heat released by the water that starts at 100 degrees Celsius but stays in its liquid form. And this is why that steam burns are much more severe than hot water burns. So for a given amount of material, the heat for a phase change is typically much more than the heat for a temperature change.